Module 3, Lesson 5, Romberg Integration. For this module, we will be discussing again yet another numerical integration technique. But this is quite different from your previous Newton Cotes integral approximation process. This particular Romberg integration is introduced with the use of an extrapolation technique. Then I will show you the different truncation errors that often occur on these different integral approximation techniques and how to do extrapolation process. And the condition will simplify then our solution by creating an extrapolation table and evaluating a sample problem using Romberg integration. The Romberg integration basically is different from your other numerical integration technique, whereby it transposes or converts whatever complicated function you have on an nth order interpolating function. This particular technique is designed more or less to attain an efficient integral approximation by comparing previous integral results that are inaccurate. Okay? Although this inaccuracy comes from error, we could actually mathematically manipulate in order to end up with a more accurate integral approximate value. The method uses two estimates of an integral value in order to compute for a third integral value. One integral estimate is considered to be the more accurate approximation, while the other integral estimate turns out to be the less accurate integral estimate. And upon using this integral estimates, we will come up with a even more accurate approximation. The estimate and error is often associated with errors that usually apply or are seen on these different techniques. For an trapezoidal rule, the error is often associated based from the number of segments, much like any other technique. As noted, the whole concept behind Romberg integration is to come up with an integral approximation that is very accurate, which is basically seen from the previous concept that if you have an integral estimate and then you add its calculated truncation error, you would end up with a very accurate integral estimate, whereby your I turns out to be the exact integral value. Your IH here on the formula is the approximate integral value from an n segment application using any technique. No? In this case, I just sampled out the trapezoidal rule. And then EH is the truncation error associated with your technique. Again, this may be from any other technique. What are these truncation errors that eventually eventually we need to add in order to have a more accurate integral estimate? From a given particular point of view, for a local truncation error for a trapezoidal rule, for example, this is the formula. This formula is relevant if your given polynomial or your given function turns out to be curved rather than a straight line. If your given function is a straight line, this technique is very accurate in approximating your integral value. However, truncation error occurs if your given function turns out to be curved, either trigonometric, exponential, or even polynomial, higher order than 1, then definitely there would be some sort of truncation error. And this particular formula was accumulated using the Taylor series expansion. Okay, this particular error lies somewhere between the interval a to b. This truncation error indicates that if a function being integrated is linear, then this trapezoidal rule, as I've mentioned to you, would be very accurate. Okay. Otherwise, for functions that are of higher order in derivatives, like curve function, eventually there would be some sort of error occurring. And this is the amount of error incurred when using a single trapezoidal rule. Hence, if you're using multiple application trapezoid rule, you have to sum up these individual errors that are often associated with each trapezoid, eventually giving you a formula much like this. Okay? So basically, you don't need to bother solving for that because we won't be solving for any truncation error here. But rather, I'm showing you that each technique is often associated with an error, which is why each technique eventually requires more segments. In order to reduce this error, the whole concept is to simply increase more segments, okay? Because it's simply very difficult to evaluate some functions when you want to establish the truncation error, okay? As observed on this particular formula, it requires you to evaluate the average second derivative integral, no, of your given function. So that means getting its second derivative and dividing it by the limit a to b, and then, of course, multiplying it by your factor here, no? Okay, so yun siya. So which is why it's a bit impractical to actually evaluate for the truncation error. Okay, so the whole concept of this basically is manipulated through your Romberg integration without actually the need for computing this error, no? For a 1/3 rule, this is the truncation error that is using a single parabolic function or a second order function. And again, that error accumulates the moment you end up using multiple application 1/3 rule. And again, this formula was simply evaluated through the use of your Taylor series expansion. No? This time, the technique requires that you evaluate for its average fourth derivative integral. So not just the second derivative this time, but rather the fourth derivative. So as seen from the formula, if my given function turns out to be too complicated, obviously obtaining its derivative would also make it complicated. So which is why practically speaking, the simplest way in order to achieve a more accurate integral estimate is to simply increase the number of segments rather than computing for the truncation error, no? Which would eventually give you a harder time because you need to solve for the fourth derivative of your given function. This is the truncation error this time for a 3/8 rule. Using a single 3/8 rule, this would be your error. And again, that error accumulates the moment you use multiple application 3/8 rule, which should eventually give you something like this formula. And again, requiring you an average of fourth derivative integral, okay, for the 3/8 rule. Now, for the Boole's rule, a single Boole's rule eventually also includes a certain truncation error, especially if you're trying to estimate integral values that are not in the shape of a fourth order interpolating function. So the error for a single Boole's rule eventually turns out to be like this, whereby, again, this is eventually later on accumulated when you're using multiple application 3/8 rule, no? Which should eventually yield something like this. So giving you like this time an average 6 derivative integral, no? So you need to have that average 6 derivative integral in order to establish this error. And again, no, the best method there is to simply apply a multiple application using a lot of segments rather than creating or computing for this truncation error. Okay. Now, one beauty of the Romberg integration is that it evaluates a more accurate integral estimate using this particular process called extrapolation. Under extrapolation, it's basically an error correction technique whereby you get to improve your numerical integration on the basis of the integral estimates that you already have or have computed. This mathematical manipulation of your integral estimate comes from this given formula derived by Richardson's. So, ayan, you know, notice that you end up comparing two integral estimates, one called IH1, the other one called IH2. Okay, so this basic error is estimate actually improves your integral estimate depending on how many integral estimates you do use in the extrapolation process. So the whole concept involves in if you're using more integral estimates that were evaluated using different segments, using a single technique, then you could, based from the formula, improve the integral estimate better by manipulating your calculated integral estimates that contains errors and use this formula to improve that. So the improved version of, or the simpler version of the formula, that is, if the new step size is now half the previous value, would turn out to be more or less like this. Okay. Again, what is IH1 is the integral estimate using the step size H1, which is considered to be less accurate. How do I know that H1 is less accurate? Because of this condition. A smaller step size, we know that from the previous solutions that we've had, no? More segments gives us more accurate integral estimate. And upon doing so, if you use more segments, you end up having a smaller step size, meaning a smaller step size also yields a more accurate integral estimate. And as seen here, H2 is smaller than your H1. Therefore, we expect that IH2 would be your more accurate integral estimate, while your IH1 is considered to be your less accurate integral estimate. Now, your extrapolation condition states that the new step size must be half the previous value. This condition must be satisfied at all times so that this formula may be applied. Note that on the formula, you have an extrapolation order K, which has a minimum value of 2 when you're comparing two integral estimates. This extrapolation value increases as you manipulate and extrapolate more integral values. I'll show that to you later on how to apply that K. So accordingly, you could simplify your solution on your Romberg integration by creating what you call an extrapolation table. Okay, this is an extrapolation table. On your extrapolation table, you provided a column for your number of segments. You provided another column for your step size or spacing. You provided another column for your integral estimates. Okay? Okay, in this case, there are 4 integral estimates that satisfy your extrapolation condition. Okay? And you usually write down the integral estimate starting from the most accurate integral estimate down to the least accurate integral estimate. So shown here on the table, if I compare all 4 integral estimates, IH4 is the most accurate integral estimate. Followed by IH3 is the next most accurate integral estimate. And so on and so forth, which means that IH1 turns out to be the least accurate integral estimate. Okay, and then what do? You compare the integral estimates using the extrapolation formula and evaluate for its value. So if I compare IH1 with IH2, I know IH2 is the more accurate integral estimate, and IH1 is the less accurate integral estimate. I improve that integral estimate, I'd end up with this notation IH12 now. Okay, next, I improve the integral estimate for IH3 and then use IH2. Again, more accurate is your IH3, while your less accurate now would be your IH2. Applying the extrapolation formula, I could evaluate and improve your integral estimate. Okay, next, I improve the integral estimate this time using IH4 along with your IH3. So we know that IH4 is the more accurate integral formula, integral value, while as your IH3 is the less accurate integral estimate. And then solve for IH34. Note that the extrapolation order applied here are all 2. Okay? Okay. Now, you could further improve these integral estimates, these 3 integral estimates that we now currently have, and improve them further. Okay? So upon improving them further, your extrapolation order now increases by 1. Always remember, this integral estimate would be more accurate than this integral estimate. So IH23 is more accurate than IH12. Okay? So again, applying the extrapolation formula using an order now of k equal to 3, solve for this new integral estimate, this improved integral estimate. Likewise, we do that same for the next pair, which is IH34 and IH23. This now, we know IH34 is more accurate and IH23 is the less accurate. Applying the extrapolation formula with the k value of 3, I end up now with the notation IH234. And then finally, improve these last 2 integral estimates at an extrapolation order this time of k equal to 4. Again, this IH234 is more accurate and this IH123 is the less accurate integral estimate. Using the extrapolation formula with k value equal to 4, you'd end up with this final improved value of your integral estimate. Okay? So that's how you create the extrapolation table. Let's try that out. Among all the previous Newton Cotes integral approximation technique, you've obviously noticed that the trapezoidal rule turns out to be the least accurate among the 4 techniques, no? Okay, so let's try to improve our trapezoidal rule estimates. Remember, this technique may be applied on any process, no? Nakuha ba? You may apply it on 1/3, you may apply it on 3/8, it doesn't matter as long as your extrapolation condition is satisfied. Okay? You will be able to improve your integral estimate. Okay, so what integral estimates do we then consider when using, let's say, trapezoidal rule for this given function? Always remember the extrapolation condition. Okay, so under the extrapolation condition, your new step size must be half the previous value. Okay, so let's say I use the initial solution that I have using trapezoidal, using one segment, no? One trapezoid, which obviously contains a lot of error. Okay, we know that the integral estimate there is 0.1728. Okay, we'll then use that integral estimate and cut down your step size by half its value. In order to do that, I need to double the number of segments. So upon doubling the number of segments, you end up with a step size of 0.4, which is half your previous value. Okay. And using this, we ended up with an integral estimate now using trapezoidal rule of a value of 1.0688 square units. Okay. So if I further subdivide this step size by 2, I would need to double my number of segments again. Upon doubling the number of segments, we did this already, no, under trapezoidal rule on the previous video lesson. Our step size now is 0.2. Our integral estimate now is 1.4848 square units. So obviously we managed to improve a lot, no, by increasing the number of segments. Unfortunately, it still fell short of our actual integral value. So I'm going to use lastly, we did 8 segments, doubling this number of segments, ending up with a step size now of 0.1, which is half your previous 0.2, with an integral estimate of 1.6008. Okay, so I'm going to use these integral estimates and try to improve this integral estimate using the extrapolation formula without using the truncation error. No? Okay, so what then would be my entry value on my table? The entry value on your table would now appear like this. So I've written it down starting from the most accurate integral estimate down to the least accurate integral estimate. Okay, and then I start off solving the improved integral estimate for k equal to 2. Okay, on the bottom 2 integral estimates. So I end up now with a solution like this. Okay, more accurate, of course, is 1.066 plus 1 all over 2 raised to k, which in this case is 2, 2 raised to 2 minus 1, multiplied with the more accurate integral estimate minus the less accurate integral estimate. Okay, so 2 squared is simply equal to 4, so that would mean 4 minus 1. This would simply mean 1/3. Okay, and you end up with an improved integral value now of 1.3675. If I compare this answer to the previous two estimates, which is 1.0688 and 0.1728, this integral estimate by far is more accurate because this is closer to my true integral value of 1.6405. Okay, so definitely it was improved. Listen then, in fact, if you look at this and recall the value, this is your integral estimate at n equal to 2 using 1/3 rule. So ano nangyari? What happened? Your accuracy improved now and is now at par with your 1/3 rule, just by simply manipulating your integral estimate. Let's try to do that again. No? On this integral estimate now, we know that 1.4848 is more accurate than 1.0688. Applying the extrapolation formula gives us this solution with an integral estimate value now of 1.6235. So again, notice, no, if I compare all three integral estimates that are used here on your solution, you end up with 1.6235 to be more accurate than the previously calculated trapezoidal rule. And I'm just manipulating my integral estimate. And again, no, you will notice, if you recall correctly, this is your answer for the Simpson's 1/3 rule at n equal to 4. So meaning at 4 segments, you manage to create a very accurate integral estimate out of your trapezoidal rule estimates, which are not very accurate. No? Okay, let's do it one more time on the last integral estimates, pair of integral estimates. 1.6008 is the more accurate integral estimate as compared to 1.4848. Using now our extrapolation formula, you would end up with this solution with an integral estimate now, improved integral estimate of 1.6395. And again, if you're very observant, this is your Simpson's 1/3 rule integral estimate at n equal to 8. So notice, no, all our integral estimates now became at par with your 1/3 rule just by simply mathematically manipulating our integral values. Okay, so if I place this on our table, you'd end up now with this solution on our table. So nalagyan ko na ng values yan. And again, continuing the extrapolation technique until there's only one integral estimate left. So we'll start off again using the values on k equal to 2 column. The last two integral estimates that we have using the extrapolation formula again at a k value equal to 3. Ending up with a solution now for k equal to 3 like this. So this is now the solution for your IH123. Using the formula, you'd end up with the more accurate 1.6235 plus 1 over 2 raised to 3 now, minus 1, 2 raised to 3 is simply 8 minus 1. So this is simply 1 over 7. 1 over 7 of what? The more accurate integral value minus the less accurate integral value. So you end up now with an integral estimate of 1.6601 square units. Applying that same concept on your integral estimates of 1.6395 and 1.6235, you'd end up now with an IH234 equivalent to this particular solution with an integral estimate, improved integral estimate of 1.6418. Okay. And again, if you try to compare all three integral estimates there, you would notice that this is more accurate than these integral estimates that you have previously computed. So when we place this on the entry of our table, it would then now look like this. Okay. And finally, using k equal to 4, the extrapolation order k equal to 4 will then try to improve these integral estimates Again, 1.6418 is the more accurate integral estimate as compared to 1.6601, which is the less accurate integral estimate. Solving now for the integral estimate at k equal to 4, you'd end up with this solution, which is now 2 raised to 4, which is basically 16 minus 1. So it's like 1 over 15 only. Okay? So ending up with an improved integral estimate of 1.6406. Okay? Note that the final answer, or the accurate answer, no, or basically the actual derivative of your given function was manually computed last time using classical integration on one of the on the trapezoidal module, ending up with a value of 1.6405. Notice how close my integral estimate now against my actual integral value, which is this. So showing you that you do not need that truncation error formula to come up with a very accurate integral estimate. So notice, it's already very accurate. We just manipulated our integral value using what? The Richardson's formula over and over. Make sure that your extrapolation conditions are satisfied when comparing your integral estimates under Richardson's extrapolation formula. So completing then the table now, your table now would appear like this, ending up with the final integral estimate value of 1.6406, which we know to be very accurate already since it's very close to our actual integral value. So yes, you could actually derive a more accurate integral estimate without the need for the truncation error. In this case, for the trapezoidal rule, it's the average second derivative. No, you need to have that average second derivative integral in order to evaluate for the truncation error and add that onto your integral estimate. No? But as seen from this concept of Romberg integration, you don't need to solve for any truncation error because this technique may be applied to any technique. It may be applied to 1/3. It may be applied to 3/8. It may be applied to Boole's rule as long as you satisfy the extrapolation condition. Okay? So all integral estimates must satisfy the extrapolation condition. Otherwise, that formula will not work. Nakuha? Follow, I hope you're able to follow the Romberg integration. No? So that covers Module 3, Lesson 5.